everyone. So for those of you who don't know me, I am Ms. Hu, your physics teacher. So in this video, we're going to go through an overview of Newton's universal law of gravitation. So this is the first topic in KSSM chapter 3, which is chapter 3 is on gravitation. Now, just to let you know, I've actually just conducted a free lesson on this. If you'd like to join my free lesson, do check out the link in the description below. But something went wrong with the recording, which I wanted to use for my YouTube channel. And I didn't want to put up a faulty recording, so I'm actually retaking the video of the lesson all over again. I actually wanted to put up the lesson recording because I tend to speak more naturally, and of course it helps when I address students and answer their questions. But since the recording failed, never mind, we'll just get to this. Okay, so rant over, let's get started. So what we're going to cover in this lesson is Newton's universal law of gravitation, and this is just going to be a general overview to give you an introduction to this particular law. Now, what is this law about? Right, so before we go into understanding what this law is about, let's just have an understanding in general about the concept of gravity. So what we have here on this slide is, okay, space, and we've got, okay, I know there's a lot of colored blobs, so just for context, all right, this is the sun, right? And let's say the blue color blob is planet Earth, and the green color blob is, for example, the moon, and that red color blob is some other planet somewhere. Okay, we'll ignore the red planet for now. In fact, I'm just going to remove it to prevent you from getting distracted. Okay, we already know that there is an attractive pull. There's an attractive pull between the heavenly bodies. Now remember that in physics, when we use the term body, we're not referring to a human body or animal body. Okay? Bodies are anything that has mass. So these, for example, would be the heavenly bodies or the celestial bodies, because we see them in the sky, right? So we know there's an attractive force that exists between, let's say, for example, the sun and the earth, and that's what keeps the planet in orbit. So the planet is, of course, orbiting around the sun, and one of the factors which affect the orbit is, of course, the gravitational pull of the Earth towards the sun, right? And even the moon, there's a gravitational pull between Earth and the moon because, well, Earth has gravity, right? And it should make sense. And now the thing is, what we're going to learn in this topic is, what is this gravitational pull and how do we calculate it? Because you have to remember, in physics, we love to calculate everything. So one of the factors that affect the gravitational pull, of course, is the mass. And it should make sense, right? The greater the mass of an object, the greater its gravitational pull. Besides seeing this among the heavenly bodies, you can actually find that there is gravitational force even between objects. For example, on Earth, like let's say, for example, okay, we've got this object and we've got this object. Is there a gravitational pull? Yes. Even between our body with something else, like, oh, is there a gravitational pull over here? Yes, there is. But the reason why we don't feel or experience this gravitational pull is because the mass is too small. That's why we study gravitational force at an astronomical level, because the mass, for example, the mass of Earth is huge. The mass of the sun is, gigantuous, right? So that enables us to experience that gravitational force. So the greater the mass of an object, the greater its gravitational force. Makes sense, right? So mass is definitely a factor. Now, besides the mass being a factor, so is the distance between those objects. That's why I had that red blob just now. Let's put it back, just for context. Let's say this is another planet, right? And if it's further away from Earth, then it should make sense that, yeah, because the distance is further, the gravitational pull will also be less. So these are the two factors which mainly affect the gravitational pull between two objects, right? Okay. Or just to explain, by the way, like, on Earth, we do see some objects with a gravitational pull between them. That's magnetic force. In this case, there's no magnetism here, so that's why you don't see any attractive pull. Okay? But yes, there is also magnetic force that causes objects to be attracted to each other, but that will be a topic for another day. So, who was the one who discovered this force? Well, none other than Newton, and that's why he's come up with Newton's universal law of gravitation. This is the definition of Newton's universal law of gravitation. So I'll just write here, def, this is the definition. Okay, the gravitational force between two bodies is directly proportional to the product of the masses of both bodies and inversely proportional to the square of the distance between the centers of the two bodies. So, such a long story. What does that mean? Actually, it's very simple when you break down the sentence, right? Because if you see, right, it's related to the two factors which we have just learned about. We've got the masses and, of course, the distance. Let me just put that a little bit lower. I don't want to block the word. Whoops. Let's make it straight. So, to write this out mathematically, let's say F represents a gravitational force. Okay. We know that the greater the mass, the greater the gravitational force. But it's not just the it's not just a mass of one object, it's a mass of both objects. And in this case, Newton discovered that it is dependent on the masses of both objects. And the relationship is the product of the masses. So I've written here M1, M2. What's M1 and M2? So let's say these two objects are experiencing a gravitational force. So M1 would be the mass of the first object. So I'll just write this as mass of object 1. And M2 would be the mass of the second object. So we'll write here as mass of object 2. Besides mass, Newton also discovered that relationship between force and the distance. So now, remember, the greater the distance, the lower the force, right? And he found a relationship to be inversely proportional. But it's not just a direct inverse proportional relationship. He found that the gravitational force is inversely proportional to the square of the distance. That's what it means when he says to the square of the distance. And why between the centers of the two bodies? It's not from surface to surface. Now, I did draw earlier surface to surface. I'm going to correct it now. So I just did the surface to surface just for explanation. So let's do it more correctly right now. It's taken from the center of the masses. So remember that whenever we calculate anything to do with mass, like even when you have to draw the weight line of an object to, downwards, it's always drawn from the center of mass because that's where the mass is focused on. So if we have to convert that mass, the scalar mass, into a vector version of a force or weight, you must take it from the center of mass, or also known as center of gravity, because that's where the mass or the weight acts from. And in this case, okay, that was not straight. Let's try that again. And so because this is a force that's acting due to the mass of the object, that was a terrible line, it's acting from the mass of the object. That's why we take it from center of mass to center of mass. So coming back to the formula, that's why we don't measure distance from surface to surface. We measure the distance from center of mass to center of mass. Or, well, assuming that it's a uniform distribution, then yes, from the centers of the two bodies. So this R that I've written here represents this distance between the centers of the two bodies. That's what this R represents. Now, of course, we can't just leave it in the relationship form. So we will combine these two, and that's what Newton did, of course. Combine them into a formula where F is on one side, and of course, because F is directly proportional, so M1, M2 is on the same level. R is the fraction, beneath the fraction, so that goes at the bottom, R squared. But you see, the force is not equal to the product of mass over the square of the distance. What they did discover, though, is that whenever they calculated the gravitational force between different objects with different masses, between, for example, say Earth and Moon, Earth and the Sun, other planets, for example, they found that they seem to come up with a constant value that relates this value of the force to the mass and the distance. So because this value is fixed, no matter what objects you're calculating, this has been given a name of gravitational constant with the symbol G. So what is G? G is the gravitational constant. Now remember that in maths, The word constant is representing a value. For example, if we look at a circle, the ratio between the circumference and the diameter of the circle is pi. Pi is a constant value of 3.14159, and so on. And it's the same value no matter the size of the circle. So we use the word constant in maths to represent these kind of fixed values, that recur again and again, regardless of the situation, for that particular type of object. So in physics, we use the word constant as well. So it's a mathematical constant, but we make it into physics. And because this particular value is the same regardless of whatever objects that are calculated, and this is based on gravitation, the name of this constant is gravitational constant. So the value of this gravitational constant is fixed at 6.67 times 10 to the power of -11 Newton meter squared per kilogram squared. Now, if you're wondering why is the unit so complicated, it is actually derived from this formula, because if we were to rewrite this formula, making G the subject, you'd have FR squared over M1, M2. So F is Newton, R is meter, so squared, meter squared, and then kilogram, kilogram. And that's where this unit is derived from. Now, if you feel like, oh gosh, there's no way I can remember this value, don't worry. This value is given in your formula sheet for SPM. I'm just going to write this clearly, this -11. So this value is given, you don't have to memorize it, and you don't have to worry about the unit. Yeah, this value with the unit will be provided in the formula sheet at the beginning of your SPM paper. Next, calculating the gravitational field of G. So what does it mean when we say calculating the gravitational field G? In this case, we're referring to calculating the gravitational field or gravitational acceleration of the body. So for example, for planet Earth, we know the value of G is 9.81 meters per second squared. But how do we get that value? Of course, through experiments and calculation. But you also find that there will be some questions where you are required to calculate the value of G for other unknown planets, and they will give you other values that you need to be able to calculate. So there is a formula that you can use to calculate the value of G quite easily, and I'm going to show you how to derive it. Now, of course, if let's say here we are, let's see, this is all the sea, so we're going to put a person here. Now, the gravitational force that exists between the person and the planet, of course, from center to center. Okay, that's not a straight line. Let's try that again. From center to center. This is the gravitational force that exists, and this is based on the same formula that we've just learned, which is F equals G M1 M2 over R squared, where R is the distance between the person and the center of Earth. M1, M2, of course, refers to the masses of both. That means, let's say, for example, M1 is the mass of the person, and M2 is the mass of the Earth. And F, of course, is the force that exists between them. But we also know that the gravitational force is weight. So if let's say we want to calculate the weight of the person, the very simple formula is just W equals mg, where W is the weight of the person, and weight exists because of the gravitational pull of the Earth, right? So m is the mass of the person, and g is the gravitational acceleration exerted by the planet onto the person. In this case, you should be able to see that the gravitational force that exists here is equal to the weight of the person. So we can relate these two, F equals W. Okay, I'm just going to put numbers here just to emphasize, right? So these two forces are actually the same. Now the mass used in the weight formula is the mass of the person. So this is actually M1. So we're going to do side-by-side substitution. G M1 M2 over R squared equals to M1G. And you can see from here, we can actually cut M1. So I can rewrite this formula as G on the side to make it G M2 over R squared. But to put an M2 here is a little bit weird. Now M2 refers to the mass of the planet. So typically, we don't put it as M2. This is normally written as a capital M. So we're going to change this into capital M, where M is the mass of the planet. And this is the simplified formula which you can use to calculate the gravitational field of a planet. So if you are required to solve a question like that, they would normally give you the mass of the planet and its radius. Now if you're looking at R, like, wait, isn't the radius from the object to the center of the planet? Yes. But do you need to take into account this little height? No, because the height here is so negligible that you can just ignore it. You can just take the value of R as the distance from the center of the planet to the surface. So that means this R is actually the radius of the planet. The big M is, of course, the mass of the planet. And G is what we have covered in the previous slide, which is the gravitational constant, that 6.67 value. Okay, so this is how we calculate the gravitational field of any planet. But what if you are required to calculate the value of G at a height above the surface? So, for example, if we have, let's say, an airplane. So I'm just going to draw a plane here. Plane, flight, plane, airplane. Okay. So obviously, the plane is not on the surface of the Earth. And one thing you should know by now is the higher we go from the surface of the Earth, the lower the strength of the gravitational field. So how do we calculate that? Let's say the plane is flying at a height above the planet, at a value of h. Taking the formula just now of G equals Gm over r squared, you just need to modify this formula. We know that r is the radius of the planet. So remember that G is calculated from center to center. So that means the R is not just R to calculate the G at this point. That means what we're doing, by the way, in case you're wondering, is we're counting, oh, how much is the G of this planet here? Planet blah. G of the plane. So you need to just be able to modify this formula and put R plus H squared. And that's how we modify the formula. So the purpose of my going through this is because this formula is provided in the formula sheet, this one. So I'm just going to highlight this formula. Okay, that looks terrible. I'm going to try that again. Let's be straight lines again. Looks so much better. So this is provided, so is this, right? But this formula of G equals Gm over r squared, even though it's, well, because it's simplified, actually this formula is not provided. So I'm just going to put a big star, because if I put a cross, it looks like you can ignore it. No, it's not provided, so you actually need to memorize it. But what if you feel, oh, there's so many formulas to memorize? Then it helps if you know how to derive. So if you could remember to take this formula, which is given in the formula sheet, and relate it to this formula, you can actually work out the formula to calculate the gravitational field. So what I'm showing you here is you have to be flexible in being able to come up with a new formula, especially if it's not given in the formula sheet. And once you know this formula, you need to know how to modify it so that it will be able to, you'll be able to calculate something like this. Because G, using the r squared formula, is at the surface of the planet. At the surface of the planet. But what if you're counting the G for an object that's above the surface? For example, the plane, a space shuttle, satellite. Then you need to modify the formula by putting it as R plus H. Okay, and finally we come to the last slide for this lesson. How G changes with the radius of the planet. So what we have at the bottom here is the graph that shows how the value of G changes, and this can be and we come to the final slide in this lesson. This graph shows how the value of the gravitational field G changes with the radius of the planet. Now this graph at the bottom is taken from your textbook, and it just shows how the value of G changes. So let's look at the first part. So between 0 and r, and what's r? R, the capital R over here, refers to the radius of the planet, in this case planet Earth. Oops, I think I'm using the wrong pen. Let's try that again. Planet radius R, capital R. Small letter r refers to the position or the distance where we are actually measuring the value of g. So say for example, if we are measuring the value of g at this, like from, from coming from the center, okay, this means it's this radius. Let me use a proper circle so that it is a lot more obvious. Otherwise, it's just what? Okay, so imagine that this point, whoops, let's make this transparent. Okay, assuming that this point is the center of the Earth, right? So this circle now represents, okay, that inner sphere inside the Earth, and we want to calculate the g at this point. What this graph shows us is that the value of g increases as it comes, as we're measuring the distance from the center of Earth. So at this point, this means that at the center of Earth, the gravitational field value is 0. As we move away from the center of the Earth, the strength of the gravitational field increases, and it's a linear increase. Now, why is it a linear increase? It's because, okay, looking at this circle, if this is the radius that we're referring to, or rather the distance, small letter r, the mass is only what is the mass of the planet within this smaller circle. That means inside here. Outside, we ignore. So taking the value of the product of g is the gravitational constant, 6.67, that value, multiplied with the mass within this circle over the distance here squared, okay, we find that the smaller the value of r, the lower the value of g. And as the value of the distance increases from the center of Earth, let's just change color here. Okay. Again, just like before, the yellow square, now it's your yellow circle, now looking at the blue circle. That means taking the mass only within this blue circle for the calculation, and the radius, or rather the distance, taken up to that blue circle only. Okay. Taking that value of g times the mass within this circle over this r squared, of course, you find that it increases at a linear rate as we go from the center of Earth towards the surface of the planet. And the value of g is the greatest at the surface. But you find that suddenly, hey, the value suddenly changes, it declines very sharply as the distance increases beyond the value of the radius r. Why? It's because the mass doesn't change anymore. So say we take at, let's change color. Beyond the surface of Earth, like at this white circle over here, we find that the mass of the Earth doesn't increase. Like over here, the yellow circle to the blue circle, the mass is not the same within those circles. The mass is actually increasing. But once we go beyond the surface of the Earth, the mass doesn't change, right? The mass already has reached its maximum, so m doesn't change, although the value of the distance changes. And that's why the value of g decreases, because if we look at the formula, right over here, g equals gm over, I'm just going to put it as small r in this case, r squared. The mass is already fixed. It already has reached the maximum no matter how much larger this value of this small r is. Right? So as m increases, oh sorry, right thing. So because m remains the same, as the value of the distance increases, the value of g decreases, and we find that it's an inversely proportional relationship, and that's why beyond the radius of the Earth, the value of g drops. So this is what this graph is showing. When it says value of g directly proportional to distance from the center of the Earth for r less than r, the capital R in this case refers to the radius of the planet, or in this case, planet Earth. So as long as the distance is less than the radius of the Earth, we find the relationship is increasing. It's directly proportional, actually. But the moment we go beyond the surface of the Earth, the value of g is inversely proportional to that distance. And that's what this graph means. So this is the end of this video lesson. And this, like I said, this video is just to give you an overview of Newton's universal law of gravitation. If you'd like to find out how to solve certain questions, do check out my other video where I go through some of the questions in one of the exercise books that we do use in the classroom. So if you enjoyed this video, please don't forget to click like and remember to subscribe for more lessons, solutions, and exam strategies by Ms. Ho. Private lessons are also available, so for more information, do check out my website, physicsrocks.com. Thanks for watching, and I hope you enjoy studying this chapter.